Assalamualaikum and good morning everyone. My name is Nur Ali Farhan bin Muhammad Ali.
Hello, Assalamualaikum. My name is Wan Fahim NAJMI bin Wan Muhammad ZAID.
Assalamualaikum and hi, my name is Muhammad Danish HAKIM bin Muhammad ZAKRI.
Hello everyone, and my name is Muhammad AMSYAR SUFI bin SHAHRUL BAHARI.
We are from Group 2, Section 2, Class 2, and today we will present our project titled Smart Monitoring in CNC Machining for BMIM1073 Condition Monitoring. The purpose of this experiment is to develop a low-cost data acquisition or DAQ system using an ESP32 together with vibration, noise, and temperature sensors. The system continuously monitors the condition of milling and lathe machines during machining. The objectives of this project are to collect real-time machine data, analyze the machine condition, and support predictive maintenance by detecting abnormalities before serious machine failures occurs. Smart monitoring is important because it helps reduce machine downtime, lowers maintaining cost, improves machining quality, and increases the overall reliability of manufacturing operations. For this experiment, we used two different machines, which are the milling machine and the lathe machine. There are three different engineering materials were tested, which are Teflon, aluminum, and mild steel. Throughout the machining process, we monitored three important parameters. And the parameters are average RMS vibration, noise level, and temperature. The most important indicator is the RMS vibration value because it provides the earliest sign of machining instability. For this project, we define the chatter threshold as an average RMS vibration value greater than 0.7 G. Once the vibration exceeds this limit, the machining process becomes unstable and chatter and begins to occur. Now, we will discuss the individual graphs for each material. In general, all graphs shows the same trend. As the depth of cut increases, the cutting force also increases. This produces higher vibration levels because the RMS value to increase gradually. However, each material behaves differently because of its mechanical properties. For Teflon, the vibration increases slowly because it has high damping capacity. It absorbs a vibration energy effectively, delaying the onset of chatter. Aluminum shows the most stable behavior throughout the machining process. Its moderate stiffness and damping provide a balanced cutting condition, allowing it to withstand larger depth of cut before chatter occurs. Mild steel reaches the chatter threshold first. Although it has the highest stiffness, it has the lowest damping capacity. As a result, vibration energy is transmitted more easily, causing the RMS value to rise rapidly. Instead of looking at the graph values, we can understand that increasing the depth of cut increases the cutting force, which eventually causes unstable machining.
I will present of my part slide 4 combined graph. This combined graph compare all three material on the same graph. Alright, from the graph, my steel reaches the chatter threshold first on both machines. For aluminium remains the most stable material because its vibration increases more gradually. When comparing the machine, we observe that the lathe generally reaches chatter early than the milling machine. This difference occurs because the cutting mechanic of turning continuously apply cutting force around the rotation workpiece, making vibration build up faster. Meanwhile, milling use intermittent cutting, allowing the tool to create automatically lift the workpiece, which slightly reduce continuous vibration. Therefore, even with the same material, different machining process produce different vibration behavior. Slide 5, material behavior. This slide explain why different material have different chatter threshold. The first factor is Young modulus, which represents material stiffness. Higher stiffness allow material to resist deformation, but stiffness alone does not determine machining stability. The second factor is damping capacity. Damping refers to ability of a material to absorb vibration energy. Teflon has the highest damping capacity, so it absorbs vibration effectively. Aluminum has moderate damping and moderate stiffness, making it the most balanced material. Steel has the highest stiffness but the lowest damping, allowing vibration energy to travel more easily through the material. Therefore, machining stability depends on both stiffness and damping, not stiffness alone. Next is the noise analysis. As the depth of cut increases, the noise level also increases. This happens because large cutting force generate stronger vibration between the cutting tool and workpiece. When chatter begin, the vibration become stable and produce a noticeable increase in sound level. However, noise alone is not the earliest indicator of chatter. Normally, vibration increase first, followed by noise. Therefore, noise is useful for confirming chatter, but vibration monitoring provide early for detection.
For the temperature analysis, the graph shows that temperature also increases as the depth of cut becomes large. This is expected because deeper cuts create greater friction between the cutting tool and the workpiece. However, temperature rises more slowly than vibration and noise. This is why temperature is called a lagging indicator. By the time temperature rises significantly, chatter has usually already started. Therefore, temperature monitoring should be used together with vibration and noise to obtain a complete understanding of machining condition. This slide explains why using multiple sensors is more reliable than using only one sensor. Each sensor detects different aspects of machining. The vibration sensor detects instability first. The noise sensor confirms the development of chatter. Finally, the temperature sensor detects heat accumulation caused by prolonged unstable cutting. Combining all three sensors reduces fault alarms and produces a more accurate diagnosis of machine condition. This is the principle behind smart condition monitoring system used in modern manufacturing. Now, alarm zones. To improve machine safety, we divide machining conditions into 3 alarm zones. The green zone represents stable machining where vibration remains below the warning level. The yellow zone indicates that vibration is increasing and the operator should monitor the machining process carefully. The red zone means chatter has occurred. At this stage, machining should be stopped and cutting parameters such as the depth of cut or spindle speed should be adjusted. Using alarm zones help prevent poor surface finish, excessive tool wear, and machine damage.
So based on our experimental result, we recommend using depth of cut for different materials. Using one fixed depth of cut for every material is not suitable because each material has a different chatter threshold. For example, my steel reaches chatter earlier than aluminium. If the same cutting parameters are applied to all kind of material, some of the material may become unstable, while others remain safe. So in that aspect, material-specific machining parameters improve machining quality, increase tool life, and reduce production costs. And this table summarizes the chatter threshold for each material on both machine, lathe and milling. We can clearly see that mild steel reaches chatter at the smallest depth of cut, while aluminium, on the other hand, remains stable until a larger depth of cut. The comparison also shows that the lathe generally experience chatter earlier than the milling machine. This summary helps engineers select suitable machining parameters based on the material and the machining process. So in the conclusion, we learned 3 important lessons from this project. The first one, different material properties directly affect machining stability because stiffness and damping influence vibration behavior. Second, RMS vibration. RMS vibration is the most effective early indicator of chatter. And finally, combining vibration, noise, temperature sensor provide a more reliable condition monitoring system than relying on a single sensor. Overall, this project demonstrates how smart monitoring can improve machining quality, extend tool life, and support predictive maintenance in modern manufacturing. That will be all from me. Thank you for your attention.